So we had made it up to arc pressure. That's up to the point of the quiz today. So this is unrelated to a quiz. I mentioned to you that when the current was too high, the spray transfer had a very long tail that started to rotate. And nobody knows why it rotates, but it rotates. Let me show you how it does. This is a video from Fronius. It's very grainy, but do you get to see how the arc goes around? We also did our own, our own video, and unfortunately we didn't give it like high enough frame rate. So, but you're gonna see how it looks too in our own lab. There you go. Here's the arc. Definitely kind of some sort of a spray transfer, but spray transfer is supposed to be like straight, like a laser beam going into the plate. And this thing is rotating, going around. And we were using 5,400 frames per second. That's fairly high. We should have been using 20,000, but it's too easy to say after it was done. Here you get to see the weld pool. And when we study penetration, you're gonna see that in this case, look at this. The arc length is long, it reaches under the surface, right? We're gonna see penetration mechanisms later. So that's rotating transfer. And in some cases it's used in commercially, very seldom. That is the case when you want to go crazy high in currents. Considerations of the gas. Most people, and this is from the Lincoln MIG guide, more people say, oh, here we have this thing that it has like as if I'm poking my finger into the plate. Many people would say, oh, that's the argon penetration. But in reality, this is not done by the argon. This is because argon gives you spray transfer, and the droplets that come actually can penetrate, cutting in, and those droplets dig this distinctive pattern, right? So yes, it's associated with argon, but not because argon has any magic property for penetration. Is because argon has the magic property of giving us the spray transfer that we don't really understand exactly why, but it does. And then the droplets are the ones that have this mechanism. About argon and helium, it shows here, okay, let's go here, CO2. CO2 cannot have spray transfer, so we don't have a deep well pool, right? We have this kind of blob well pool, and we don't have this kind of poking with the finger effect at the bottom. The mixture between argon and helium, you see here, they indicate also that argon has pretty good, what they call wetting, has very little to do with the surface tension, although most people think so, but it has a lot to do with the heat transfer here at the toe of the weld as it's being made. And here it shows how this wetting goes progressively from pretty good wetting to not so good, really not good, and really bad, right? And the penetration changes. But the cool thing is this is done by a super talented, now he's a professor in Germany, who did this very systematic set of videos from 100% argon to 100% CO2. And you get to see, I would have liked to see what happens after 18% CO2, but you get to see that how you have a long tail with 100% argon, and how the tail gets shorter and shorter as we have more CO2. You get to see something else in this set of videos too, that is so awesome. You get to see that in 100% CO2, the droplets go pretty straight. Is exactly straight? No, nothing is ever exact, but it's fairly straight. But as we add more and more CO2, you get to see how the droplet sometimes detach to the side. In this case, well, that droplet here is definitely going to this side. In our case, for measuring the droplet temperature, we need to make the droplets pass through a hole. And the reason you have, I showed you values for droplet temperature up to 10% CO2 is oh, hold on. Up to 10% CO2 is because at more than 10% CO2, the arc is so unstable that the droplet doesn't want to go through the hole and becomes a big mess, right? And you get to see this in action here. Let's see the effect of oxygen, right? And oxygen is not like CO2, has somewhat of an effect. And these effects are not really well understood. Yeah, I can show these to you, and some people can even do some numerical simulations. Do we really understand them? The effect of oxygen is reducing the surface tension of iron when it's molten at relatively low temperatures into the melting. At very high temperatures, oxygen doesn't matter anymore. But we talked about how the transition current comes from a balance between electromagnetic forces and capillary forces. So if I have oxygen, I lower my capillary forces. Helium, right? And here I see an inconsistency. And in welding, we see inconsistencies all the time. So the Lincoln MIG welding guide suggested that with helium, we would not have this kind of finger pattern, penetration pattern that is characteristic of spray transfer. As I'm looking at these images for helium, I would say helium gives you spray transfer right, at least for my colleague in Germany. So I cannot put those two things together. These are the type of things that somebody once saw, and people have not like done a systematic study to say, okay, let's make sure we know what we are talking about. We already discussed some about the droplet temperature. Oh, about the effect of gas. I was mentioning to you before, the droplet temperature doesn't really change. Yes, you see some change here, but I believe it's fake news. But I am pretty certain that the change in the transition current is happening. So that is important because that helps us when we calculate the position rate. If instead of assuming 2500 degrees all the time, as I'm teaching you here in the class, you do it more sophisticated thing as I did for my own research, then you would see how the deposition rate is affected by this change in droplet temperature as it goes through the transition current. And guess what? Yes, when you measure it carefully, you see it. It's quite amazing. So most of the commercial brochures say nothing about this. When you see curves of deposition rate that come from research, you get to see this little blip in the deposition rate as it goes through the transition current. Flux core. Here we have self-shielded, and here we have dual shielded. You had already seen this video, and what we had seen here is how the arc was fairly unstable in the self-shielded and with higher spatter. And in the dual shielded, we were in much better shape. Still a far cry from the metal transfer you see in MIG, which is very clean, right? The fluxes in this case play games. How about subarc welding? This is new. Somebody in 1966 did some videos in Germany, and nobody did anything like that ever since. We did it in the lab. we did a few years ago with a German friend, by the way, and was a smashing success. We made a little bit of a hole in the flux bed to see the droplet. And we saw very different heat transfer metal transfer mechanisms. Here we have metal transfer in subarc welding at 500 amps. Here we have the electrode. Here we have the electrode, right? And this is a droplet. And we're going at 10,000 frames per second. This is slowed down quite a bit. See how like the droplet is deforming so much, right? And there are fluxes here. We suspect that the brighter parts are fluxes that are like on the surface of the droplet. Let's see if the droplet detaches. Okay, it detached there. What the hell is that? It's some sort of globular, but very tricky globular, right? You don't see this with your eyes. And there is many waveforms for MIG because you can see it and do your research and you can know what you're doing. For subarc welding, square wave. But the machines could do anything. Everything you do in MIG, you can do with a subarc welding machine. The only difference is, nobody knows what to do. But guess what? We did this, and not long after, waveforms have started to appear in commercial subarc welding machines. We're pretty proud of this. Let me show you at 1,000 amps what happens. Very different thing. Let's go here. We're also going at 10,000 frames per second. So let's see how this droplet detaches. Whoa. Did you see that? It's very quickly, we have kind of a whipping mechanism. It makes a cone. You see it again? Okay, I'll try to stop it if I can. Let's see. I can't. It's so difficult. But we have photos and we have published those in the papers. Okay, well, more or less, you get to see how this went to the right, and this other part that broke was having some sort of there you go. You see how it's making a turn. And this is an electromagnetic instability. This has nothing to do with rotating transfer. And this had never been observed, except in our lab. And some people, if you go way back to the papers in which they were looking at things in X-rays, they saw some photos, but they couldn't do these 10,000 frames per second. Right today, you cannot do 10,000 frames per second X-rays. So they didn't know what they were seeing. But now we see the videos. It's quite amazing. So the difference between metal transfer at 500 amps in subarc welding and at 1,000 amps in subarc welding, a world of difference. Stick welding, I showed that to you, and because I have 1 minute, how about if I show you electrode slag welding? This is a very, very kind colleague of us in Japan who gave me these videos even before he had his paper published. His paper just came out, and it's an awesome paper. He did 2 experiments. One is with X-rays, this one here. This other one is what is called a Hele-Shaw cell between 2 parallel plates. One is a glass, so he can see what's going through the glass. So let's see it again. In electroslag, there is no arc, right? It's just the molten slag, what causes the environment of the droplet. So a droplet detaches and falls. And this thing we see here, that is the molten slag. Same here. What we see here in this heart shape is the molten slag. And on top of this will be the solidified metal, and these wider wings here are what is giving it penetration to the side to melt the base metal. All right. I think I'm super happy that I could show you all these slides on metal transfer. And it's our time to stop and give you time to get ready for the quiz.